Welcome, students, to Chemistry Tales. This is Tale 16 on electrochemistry. We are on track 3, using the Nernst equation when our redox process does not occur under standard conditions, and also predicting the spontaneity of our redox reaction. The first thing we want to give consideration to is the spontaneity of redox reactions. So we've learned about how to predict cell potential, and we've said that if the cell potential is positive, it's spontaneous, and if it's negative, it's not spontaneous. So let's revisit what it means to be spontaneous. Okay, if the process is spontaneous, when we connect all of the terminals in our electrochemical cell, that means automatically, the second we complete the circuit, okay, electrons will spontaneously be generated by zinc metal, giving up 2 electrons, forming zinc ions. And then those electrons will flow through the voltmeter over to the cathode, where the copper ions will take those 2 electrons and be reduced to copper metal. From a previous slide, we were able to predict the magnitude of the cell potential under standard conditions for this reaction. We said it was a positive 1.10 volts. Okay, all right, so we want to look at an equation that's going to relate the magnitude of the cell potential to the thermodynamic parameter that dictates spontaneity. The thermodynamic parameter that tells us if a process is spontaneous or not is the Gibbs free energy change. Okay, I'm not going to go through the derivation. I'm simply going to give you the equation. But that critical equation is as follows. Under standard conditions, the Gibbs free energy change for a redox process is negative NFE0 cell. N is the number of moles of electrons exchanged in our balanced redox process. That's why it's important to balance your redox process. You have to know how many moles of electrons are being exchanged. Okay, F is Faraday's constant. This is the charge on 1 mole of electrons, and that number is 96,485. Charge is coulombs per mole of electrons. And then finally, the cell potential under standard conditions. Okay, we can predict by going to the standard reduction data tables and taking the standard reduction potential of what's happening at the cathode minus the half reaction at the anode, and we can come up with that cell potential, and that's going to be in units of volts, and a volt is unit-wise a joule over a coulomb. Okay, so just from a unit perspective, let's look at what we're going to get out. N is moles. Faraday's constant is coulombs per mole. And the cell potential is in volts, which is a joule over a coulomb. So the moles are going to cancel, coulombs are going to cancel, and you're left with the unit of a joule, which is energy, which is what we would expect for Gibbs free energy. All right, so just thinking through some logic. All right, so we know from the past that if Gibbs free energy change is negative, less than 0, that is the condition for a spontaneous process. Okay, all right, so if you look at this equation, the only way delta G is going to be negative is if the cell potential is positive, because you've got a negative term out here. Okay, all right, so when we have a redox process that's spontaneous, Gibbs free energy change is negative, cell potential is positive. This is the specific scenario that we describe for the cell as being a voltaic or a galvanic cell. And these are the ones for which the electrons just spontaneously flow from the anode to the cathode, and we can derive useful work in the form of a current. Okay, so batteries, right? All right, so the other possible sign conventions for the cell potential and Gibbs free energy change. All right, if Gibbs free energy change is positive, we know that's a non-spontaneous process. You are going to have to provide an external power source to make the electrons flow from the anode to the cathode. All right, this is the condition of an electrolytic cell. And if we do a sign analysis on Gibbs free energy change, for a non-spontaneous process, delta G is positive, and the only way delta G is going to be positive is if the cell potential is negative, because we've got this negative sign out in front. And finally, what does it mean if Gibbs free energy change is equal to 0? That means we're at equilibrium. Okay, all right, and if we're at equilibrium, and the only way delta G is going to be 0 is if the cell potential is 0. Okay, and so the way electrochemical cells work, the second you connect all of the electrodes, the electrons start flowing from the anode to the cathode, right? That just starts happening. At some point, though, on the right side, you only have so much copper ions in solution. At some point, you're going to reach a state of equilibrium, and the cell potential actually changes with time. And when you initially connect everything, that is the initial cell potential, but because the concentrations of that species and that species change over time, eventually that cell potential drops to 0 when we finally reach a state of equilibrium. Next, we want to take the equation that relates Gibbs free energy to the cell potential to do a calculation. So let's go back to our previous example of our electrochemical cell, in which we have copper sulfate reacting with zinc metal to give zinc sulfate and copper metal. Okay, all right, so we really have copper ions and sulfate ions reacting with zinc metal to give zinc ions, sulfate ions, and copper metal. All right, so the sulfate ions are spectator ions. So I'm just going to take them out of here for now. Subtract that from both sides. So there's your overall redox process. We have previously predicted, using standard reduction data tables, the cell potential for that redox reaction. It was a positive 1.10 volts. All right, so now we want to go back to the equation we just talked about. Gibbs free energy change is negative NFE0 cell. So let's calculate the Gibbs free energy change here. All right, and this is why it was important to balance the redox reaction. If you will recall, this is a 2-electron exchange. When we balance this reaction, we had the exchange of 2 moles of electrons. Copper goes from an oxidation number of 0 to +2. I'm sorry, let me back up. Copper goes from an oxidation number of +2 to 0, so that there's a change of 2 units of oxidation number. Zinc goes from 0 to +2. That's how we know we're exchanging 2 electrons. Okay, so in this equation, negative 2 moles of electrons, Faraday's constant, 96,486 coulombs per 1 mole of electrons. And our cell potential, as predicted from the standard reduction tables, is 1.10 volts. And from a unit perspective, this is important. A volt is a joule over a coulomb. So that's a joule over a coulomb. So unit analysis, my moles are canceling, coulombs are canceling, and I am left with joules, which is a unit of energy. Carrying out the math, this is going to give us a negative 2.12 times 10 to the 5th joules. Okay, the importance of this value that we've just calculated, it's a negative Gibbs free energy change. That tells us the process is spontaneous. When we connect the terminals in this electrochemical cell, the current automatically flows from the anode to the cathode. And because of the nature of the spontaneity, we call this cell a voltaic cell. We can use it to usefully use the current to drive another process. So when we do chemical reactions, it's not common that we always use the conditions of standard conditions, where any gas is at 1 bar of pressure and any solution species is at a concentration of 1 molarity unit. Technically an activity unit, but approximately a 1 molarity unit. And also temperature of 25 degrees C. There are many times when we want to conduct reactions at different temperatures, pressures, and concentrations. And so we want to be able to accurately predict the cell potential for these kinds of reactions, redox reactions. Okay, so basically, let's just think of some redox process in which we've got these reactants going to these products. It's a redox process. There's an exchange of electrons. Okay, so going back to our chapter on equilibrium and use of the reaction quotient, which looks like the equilibrium constant, but we are not at equilibrium. Okay, if we wrote a reaction quotient for this process, it'd be products C to the C, D to the D, A to the A, B to the B, where those are concentration units. Okay, so with that in mind, we want to come back to the equation that we just thought about in terms of the Gibbs free energy change. So if we are not at standard conditions, let's say we're not at 25 degrees C, let's say we're at 100 degrees C. We want to be able to predict the Gibbs free energy change under non-standard conditions. Okay, so I'm not going to go through the derivation, but what we need to do is take the value of the Gibbs free energy change under standard conditions, and then I need a correction factor. I need to correct for the slight differences that occur when I'm not at a concentration of 1 molar or a pressure of 1 bar or a temperature of 25 degrees C. So this second term here is a correction factor to our Gibbs free energy change. Okay, all right, and the value is RT ln K. R is the gas constant that we've been using regularly. 8.314 joules per mole degree Kelvin. T is temperature in Kelvin. And Q is the reaction quotient, just like we demonstrated above. Okay, so now I'm going to go through this equation and I'm just going to substitute for our delta G terms, our expressions in terms of the cell potential. Okay, so delta G under non-standard conditions is going to be negative NF E cell under non-standard conditions. Okay, delta G under standard conditions is going to be minus NF E0 cell under standard conditions. And then we've got this correction term. Okay, all right, so just rearranging some of the parameters in these equations. If you divide both sides of the equation by negative NF, and that leaves you on the left, it leaves you with the cell potential under non-standard conditions equals the cell potential under standard conditions. And we took this RT and divided by negative NF. Okay, so now we have negative RT over NF ln Q. All right, so now if I simply throw in actual values for some of these constants, remember R here in this equation is 8.314 joules per mole degree Kelvin. If the temperature is 25 degrees C, that's 298 Kelvin. We know Faraday's constant, it's this 96,485 coulombs per mole. Okay, and I'm going to also convert from log base E to log base 10. And that conversion is this. So if you multiply all those constants together, all of those constants come up to a value of RT over F, which is 0.0591. So now I've got a nice clean equation called the Nernst equation, which predicts the cell potential for any redox process under non-standard conditions. Okay, so the way we're going to use this equation is we're going to use our standard reduction data tables to get the cell potential under standard conditions. And then we're going to throw in this correction term. And Q is our reaction quotient for the reaction of interest, as we've always expressed it. Okay, so now let's put the Nernst equation to use. Coming back to the example of the redox reaction we've been giving consideration to, in which we are oxidizing zinc and reducing copper. Okay, the shorthand notation for the cell we want to consider is given right here. Okay, so notice that the solution of zinc sulfate here has a concentration of 0.56 molar, and the solution of the copper sulfate is 0.035 molar. So we are not at 1 molar concentration units, so we are not under standard conditions. So we wish to predict the cell potential for this process, this electrochemical cell under these conditions. And I want to tell you that the temperature is at 25 degrees C. Okay, so we should be able to use the Nernst equation to predict the cell potential. All right, so the only thing that I probably need to work on if I'm going to use the Nernst equation, I want to calculate the cell potential under these conditions. I already know the cell potential under standard conditions. We've been looking at that value for some time. Okay, we know that's 1.10 volts. So the only thing I need here now is this reaction quotient term. Okay, so for this given reaction, once again, remember this is copper 2+ ions reacting with zinc metal to give copper solid and zinc 2+ ions. If you were to write an equilibrium constant for that reaction, okay, it would look the same as the reaction quotient, right? So Q here, starting with products, okay, that's a solid. You don't include a term. I got zinc ions in solution, so it's the concentration of the zinc ions to the first exponent over reactants. That's in solution. That's a solid. So copper ions in solution to the first exponent. So there is your reaction quotient for this redox process. And notice I am given in the data above these concentrations of my solutions. Okay, so I know the zinc ion concentration and the copper ion concentration. All right, so now it's a matter of plugging in the data into the Nernst equation. So my cell potential under these conditions is going to be that under standard conditions, that I know, 1.10 volts minus 0.0591 over N is the moles of electrons exchanged. I know that's 2 moles. And I go log base 10 and I plug in Q. Q is the concentration of my zinc ions, first exponent over concentration of my copper ions. Okay, so that term I'm going to plug in for the zinc ions. They are 0.56 molar, and the copper ions up here, 0.035 molar. So that's the ratio of the concentrations you're going to take the log of. So this should give you a value of the 1.10 volts minus, and our little correction term comes out to be 3.56 times 10 to the negative 2 volts. The units on the log term here is volts. Not the log term, sorry, the constant term out in front. Okay, so our cell potential will be a little different under these conditions. It's now going to be a positive 1.06 volts. So the Nernst equation has allowed us to predict the cell potential when we are working under conditions that aren't standard conditions. What I'd like to do at this point is to go back to our understanding of thermodynamics and tie in one additional parameter that's important to chemical reactions, the equilibrium constant. If you will remember, spontaneous processes are those in which the Gibbs free energy change is negative. Okay, those tend to be reactions that just go without us having to do work. If the reaction goes, we will produce product and we will consume reactant. And those are the kinds of reactions that tend to have large equilibrium constants. All right, so let's go through a quick little derivation that's going to pull all of the information together relating cell potentials, Gibbs free energy change, and equilibrium constants. Okay, so let's just think about this overall process shown here. Reactants A and B undergoing some kind of a redox process, and we get C and D as products. Okay, the reaction quotient for that reaction would look as shown over here. Okay, so if you created an electrochemical cell to measure the potential of this process, okay, when you initially connect all of the terminals, you would, at the initial moment that everything started, you would have a certain Gibbs free energy change and a certain cell potential. Okay, however, if you let that electrochemical cell go for any length of time, the cell potential drops off because our concentrations of reactants and products are changing. Okay, all right, so eventually we get to a state of equilibrium, okay, where those relative proportions of the products and reactants are constant. Okay, so going back to our equation that yielded the Nernst equation, we've got the Gibbs free energy change under non-standard conditions equals that under standard conditions plus this correction factor for any differences from standard conditions. So as we hit equilibrium, the value Q in this equation, Q goes to K, right? We're at equilibrium, so the value of Q goes to K. And also, as we hit equilibrium, the Gibbs free energy change goes to a value of 0. So substituting those relationships into the above equation, the delta G goes to 0, Q goes to K, and we have this equation. 0 has got to equal the Gibbs free energy change under standard conditions plus RT ln K. If we rearrange the terms in this equation, we get Gibbs free energy change under standard conditions equals negative RT ln K. Okay, all right, but keep in mind we have an equivalent expression for Gibbs free energy change in terms of the cell potential. It is negative NFE0 cell. So that value has got to equal negative RT ln K. Now we can derive a relationship between cell potential under standard conditions and the equilibrium constant. Rearranging terms and doing conversion of natural log to log base natural log to log base 10, okay, is going to give us this equation for our cell potential. Okay, cell potential is going to be that constant RT over F, so 0.0591 over N, the number of moles of electrons exchanged, log of the equilibrium constant. Okay, so we can relate cell potential under standard conditions and the equilibrium constant. So if you know K, you can calculate cell potential, or you can take this equation and solve for K. Okay, if we want to solve for K, I have to take the anti-log, and so that's raising 10 to the exponent on both sides. And so the equation to calculate the equilibrium constant is to raise 10 to the exponent NE0 cell divided by 0.0591. Okay, and I just wanted to tie everything together for a quick review slide here. So regarding the equilibrium constant and redox reactions and the Gibbs free energy change, spontaneous reactions are those for which delta G is negative. Our cell potential is positive. These are our voltaic cells. And notice if this value is positive, okay, the only way that's going to be true is when K is bigger than 1. Okay, that means we have more product than reactant. So this all makes sense. A spontaneous process just happens. We don't have to do any work to make it go. The cell potential is positive. Equilibrium constant is bigger than 1. Products are favored. Non-spontaneous processes, Gibbs free energy change positive, cell potential is negative. These are electrolytic cells, and unless we provide an external power source to drive it, we are going to have more reactant than product. K is going to be less than 1. And finally, if we are at equilibrium, the Gibbs free energy change is 0 and the cell potential is 0. Okay, so this is our final slide. Yay! We just simply want to put to use the equations we just learned about that relates the cell potential for redox reactions with the equilibrium constant. So I'm just going to review the equations. Okay, they are as shown here. All right, and let's apply this to the electrochemical cell we've been thinking about for some time. The cell where we are oxidizing zinc and reducing copper. Okay, there's our overall reaction. And we know the cell potential under standard conditions is 1.101 volts. We got that data from the standard reduction data tables. Okay, so what I want to do now is calculate the equilibrium constant for this reaction under standard conditions. Okay, so very simply, from this equation, if we solve for K, the value of K is 10 raised to the exponent shown here. Number of moles of electrons exchanged, once again, remember copper here is 2+ oxidation state, goes to copper 0 oxidation state. It's a 2 mole electron exchange. So this is 2 moles of electrons. The cell potential is 1.10 volts, and we're dividing that by 0.0591. Okay, the constant has units of volts, so the volts are going to cancel. So we are technically raising 10 to the exponent of 37.22, where we have 3 sig figs, 1 decimal place. Okay, this is going to give me a value of the equilibrium constant, which is 1.67 times 10 to the 37th. That's a very big number. From a significant figure standpoint, if I have 1 decimal place, I have 1 significant figure. So this is actually 2 times 10 to the 37th as your equilibrium constant. Okay, and so remember the equilibrium constant is the concentration of the zinc ions over the concentration of the copper ions. Okay, all right, so tying everything together for this redox process, we have a positive cell potential. It's a spontaneous reaction. Gibbs free energy change was a large negative value on the order of 10 to the 5th joules, and we have a very large equilibrium constant. So that tells us that when we connect the terminals in this electrochemical cell, it just goes, and we derive useful current from that reaction. Okay, so this ends our coverage of electrochemistry, and I wish you a good day.